we're going to get into spectroscopy. And what this is actually showing you is the different spectra of stars. And when we get on to classifying stars, this will become a whole lot clearer. But before we can get there, we really need to understand how light interacts with atoms. Now, I'm going to stop this and talk about it. Here we have light from a hot body like a star or a glowing rod like we already talked about. It's passing through a prism, and we will get a continuous distribution of light that will be a black body spectrum according to its temperature. Now, what happens if we actually have a cloud of material in front? It's cooler gas, it's passing through, and now it's being split up into its different light. So light that is passing through the cloud will either have an absorption line spectrum or an emission line spectrum. And we're going to look at why we get that and why it's useful. Now, in fact, this gives us what are known as Kirikovs or Kirikovs Laws. Different people pronounce it different ways. So, there are basically three different types of spectra that you can get. One is that an incandescent solid, so like old-fashioned incandescent light bulbs, or even a high-density gas, so a star, basically produces a continuous spectrum, a rainbow. It's all colors, and it's basically a black body. If you have a low-density gas, and it's hot and glowing, it will give you an emission line spectrum. And if you have a similar low-density gas, but it's cool, and you're viewing light from a continuous source, like a star, through that gas, you will get an absorption line spectrum. And we're going to look at why that is. But I want to make sure that we get the difference between these. So here we have the continuous spectrum from a solid or high-density gas. Here we've taken the light and split it up. If you add all of these colors together, this is actually the spectrum of hydrogen. This is going to be what you get if hydrogen is glowing. And you'll see something that's kind of purplish. And then this is what you get if you're viewing this spectrum, but the light has passed through a gas made of hydrogen. Okay, so let's actually look at these in a little more detail. So here I have an incandescent light bulb. I have the light going into a telescope, into a spectrograph, and I get this nice continuous spectrum. Then if I have a low-density gas, so here I have a low-density gas. I'm looking at the gas but not at the light bulb. Notice that my telescope is pointing up here. It's not pointing at the light. And so what I'm getting is that the atoms are being highlighted by this, they're being excited by this light, and then that light is being emitted. And it goes in all directions, but some comes towards our telescope, and we can see that emission spectrum. So the light excites the electrons in the atoms to a higher energy state. We're going to look at this in detail. And so the stuff that we get is that as those electrons jump back down in energy level, they are going to give us light at specific wavelengths. And then finally, we have that if light is between us, so now we're looking at this, and you're having the same effect. The light is hitting the atoms, it's being absorbed by the atoms, the electrons are jumping up, but then most of the light that is at the right wavelengths is being emitted not in the direction towards our telescope, and so what we see is an absorption. That light is missing. And so it's the same effect, it's to do with the line of sight that we're looking at. So for stars, what we see is something very like that. We've got this gas that's high density, and it gives us a continuous spectrum, but then it still has an atmosphere of lower density gas, and that gives rise to an absorption spectrum. But that allows us to work out what material we have in those low density layers in the atmosphere. Okay, so what is actually going on here? Here I have an atom. It's actually an electron. Here we have a proton and an electron, so it's a hydrogen atom. We have these different energy levels that the electron can be at. So we have an electron can be in n equals 1, n equals 2, n equals 3, n equals 4, and so on. At the moment it's in n equals 2, and there are photons flying past it, but it can only take a photon that will take it up to n equals 3 or n equals 4 or escape. It can't get an energy in between. So let's see what happens. We've got exactly the right energy comes along and it jumps up, but then it's going to jump back down again and emit that same energy to get back down there. And so what that does is means that we're going to watch it again. As it goes around, we've got play again. Here we go. It goes around, we've got photons coming along, they're not the right wavelengths, and eventually one comes along, it's the right wavelength, and it jumps up. Notice that it came from here. So if we were looking in this direction, we would see that photon missing. Now it's up here, it didn't emit the photon in this direction, so it's still missing. But if we were looking over here, we wouldn't have seen the original light source over here, so we'd only see that new emission from over here. I have a schematic of that, I hope. So here, this is what we just saw. We've got light comes in. If we're looking in this direction, we've got a bunch of photons, let's say it's a star. We've got all these different wavelengths, but only the wavelengths that are relevant to it jumping up to another level will disappear. Whereas here, we're not seeing the source over here that's illuminating it, because we're looking from the upper right, and so we'll only see the ones that get emitted, and so we get an emission spectrum. So we get the energy can only be the difference between the orbits, and that's what gives rise to those very simple emission and absorption spectra. And so this is the same thing again, but showing you what you actually see. So in this case, you're looking in this direction, and you see the light missing because it got absorbed, but the in-between wavelengths don't, because it can't jump at up through those energies. Whereas in this case, you're looking in this direction, and now you're only seeing the stuff that gets emitted by the electrons. And this actually gives us neon lights. So for neon lights, you have exactly this going on. You're exciting the atoms electrically, you're giving them electrical energy, and then the electrons are in high energy levels and they jump down. And technically, neon is giving you only red, yellow, and orange light. If you look at the spectrum, it's only got these red, orange, and yellow colors. It doesn't have any others, but this is what the energy levels are. This is the frequencies that you get. Whereas mercury, which is what's used in most of the tube lights that we have in our classrooms, is missing the red light. It's got yellow and green and blue and violet, but it doesn't have any red, and that's why it looks kind of sanitary. It's missing those warm colors. And then sodium that we use for street lights basically only has yellow. And here we've got different ones. So here we've got what you get for neon. Hydrogen has red and blue and purple, but when you mix those up, it gets purplish. Nitrogen looks whitish. Mercury is a bit blue, and so on. That should say the energies are different for different elements. But it gets more complicated, because in hydrogen you only have one electron, whereas in helium you have 2 electrons. In boron you have 4 electrons, and so on. And so you have to account for that in the electric field. It's really what is the energy it needs to have to be at that position. You get these different energy levels, but that means that you will have very different distribution of energies depending on the different structures. So we have these different electric fields, and that's what gives rise to those different colors in the neon lights. Then we have another thing that we can think about. As long as we're not talking about hydrogen, if you ionize hydrogen, you're just left with a proton. But if you've got helium, you can lose an electron. Woo! Photon came along, knocks off an electron, and here we have a positively charged ion. And if you've got bigger atoms like oxygen has 8 electrons, so it can be neutral. It can lose 1, 2, 3, 4, all the way up to 7 and still have an electron. And so but that also changes the electric field, because now you've lost 1 electron, you've only got 7 electrons, that changes the electric field. You lose another electron, changes the electric field again. And so, as well as being able to use the spectrum to determine what the atom is, you can also work out what sort of ions you have. Now, I just want to mention this. Hydrogen can only lose 1. We already talked about that. But we have this notation, which is basically, if it is a Roman numeral 1, it is atomic. If it loses 1 electron, it has a 2. If it loses 2 electrons, it has a 3, and so on. So, helium-2 has lost 1 electron. Helium-3 is ionized completely. You can have oxygen can go all the way up to 7, and so on. If you've got iron, the metal iron, it has 26 electrons and therefore can lose 25 and still have an electron, and so on. And so O3 is O2 plus, and we can tell the difference between all of these, because there's always more than one transition that we can observe. So here I've got a picture of the Helix Nebula, just an example of this. The thing that looks like a star in the middle right there, that was just to mark where the star really is. That's a very hot central star. The stuff that we're looking at, and so it behaves like a black body. The stuff that we see here, this is gas. The blue glow is helium gas. This glow here is also gas. So what we get, if we were to look just at the star, we should get something that looks more or less like this. Doesn't quite, but we'll come back to it. But then this star is very hot. It's illuminating this gas, and this gas is then going to be emitting those emission lines. Whereas, actually, this isn't quite like that. It's going to have absorption lines, not only because of its own atmosphere, but because it's passing through the gas in the nebula. And so coming back to hydrogen, which is our most common thing, here we've got the Lyman series, which is ultraviolet, and you can see it in terms of wavelengths that you need to have photons in. And what will be really important is this Balmer series. So this is red, and this is why things in space look red. And this is kind of violet. And this is what we really care about because we can view this in the visible. These wavelengths are wavelengths where the atmosphere causes problems because it's in the UV. Likewise here we're into the infrared. And so the Balmer series is really important. And in fact, because that first transition from n equals 2 to n equals 3 is 656 nanometers, that is red. We call that H alpha. In fact, this is what it looks like. This is a spectrum of something. So you've got something illuminating the hydrogen gas. You've got gas missing. And actually, if we plot this in terms of brightness, it's actually brightest in the violet, getting fainter and fainter through the red. But at the same time, you've got this light missing. And so you can actually measure where it's missing. And we call this line here, that's the n equals 2 to 3 absorption, is H alpha. This is 2 to 4 is H beta. 2 to 5 is H gamma. Sometimes you can see the line out here, which is 2 to 6, and so on. Normally when we draw spectra, we don't have them as nice, pretty rainbows. We plot them like this in 2 dimensions of intensity versus wavelength. Okay, so now that we've got that, we can get into the final issue that will allow us to diagnose what's going on in space, which is the Doppler effect. I'm sure you've all come across this, but this is the thing that means that when cars speed past you, they change in pitch. So they're going up in pitch as they come towards you, and down in pitch as they go past you and away from you. And so you get the meow effect. It's particularly effective when you have a fire truck that's coming towards you, the siren goes up in pitch, as it goes away from you it goes down. And light does the same thing. And it's basically that as you are moving towards an object, or it's moving towards you, although you have emitted a wavelength, the crest of that, the crest of that wave is then squished up next to the next one because the source has moved closer to you as you are seeing it. And so it will tend to make the crests look close together, which is basically shorter wavelengths. So it looks bluer. But it also means that if you're over here, this thing's moving this way. So it was over here, it emitted a wave, and then it moved and it emitted a wave. So it makes the wavelength appear longer, and that's the pitch goes down. Or in the case of light, longer wavelength is red, shorter wavelength is blue. We can quantify this, that the change in wavelength is related to the initial wavelength and the speed at which the thing is moving in a radial direction. So it has to be directly away or towards you. And so we've got the actual original wavelength at stationary, we've got how much it changes, and the radial velocity. So here I've got an unshifted spectrum, and now as I shift it, you can see that it's all shifted. This is stuff that's moving away from me. Everything is redder, everything is shifted towards the red, but the red lines are shifted more than the blue lines because it relates to the wavelength. Likewise, I have something approaching me. The blue lines are shifted more bluewards, the red lines are shifted more redwards, but the red lines are shifted more. And this is just another way of looking at this. So here I have a source, and it is emitting in all directions, and this one wavelength that's going to have a crest here, crest here, crest here, crest here. Now it's moving, and that means that it emitted one here, but it's already moved, so it was here, it's already moved to here, and now it's emitted another crest. Now it's moved to here, emitted another crest. And you can see how that then makes this have a shorter wavelength, the crests are closer together, and a longer wavelength if you're moving away. And that's it for the properties of light.